I think Helmut, okay, I think we should take now the moment to start, and is that okay, Helmut?
Sure.
So
sure.
we'll, yeah. So somewhat, I was given the honor to make the introduction of the day. My name is Mikhail Gromov, and with this being said, I would like to welcome very warmly all the participants of the IAS, Princeton, Montreal, Paris, Tel-Aviv, Symplectic Geometry seminar, to which Berlin, or more specifically the Berlin Mathematics Research Center Math Plus, has been kindly added today. Thus, welcome also to the Berlin participants. Of course, an equally warm welcome now also goes to Helmut Hofer, the main actor of the day. As I said, I'm Jörg Kramer. I'm presently chairing the Berlin Mathematical School, which is part of Math Plus and which organizes the Math Plus Friday colloquia, to which we invited Helmut Hofer today, and which eventually then led to this great event today. So before giving Helmut the word, just a few words about his person, in particular for the young people who possibly do not know him so well as many of the prestigious participants of this meeting. So Helmut received his diploma and PhD around 1918, plus minus 1 year, respectively at the University of Zurich. And after his first professorships in the US, he returned to Europe, first to Bochum, which is important for today's lecture in particular, and then back to Zurich again, but now to the ETH. So this was in the 90s. This was also the time when we get to know each other at ETH. But already in 97, he moved back to the US again, first to the Courant Institute, and from 2009 onwards to the Institute for Advanced Studies in Princeton, where he now holds the Hermann Weil chair. The list of his distinctions is very long. So for brevity, I just mentioned his memberships at the US National Academy of Sciences and the one at the Leopoldina in Germany. He was plenary and invited speaker at numerous distinguished congresses, I just mentioned ICMs and conferences. But now we have the great pleasure to have him here, and we are looking forward to hear about the Floer jungle. Helmut, now the floor is yours.
Okay, so now I have to press the right button. And so you see my screen?
Yes, perfect, Helmut.
Okay, so let me. Yeah, so dear Jörg, so thank you very much for the kind introduction. So we'll be talking about Floer, and a lot of the things I'm going to say is based on a book project about Floer with Siobhan Roberts. She is an author, science journalist, and senior editor on computing of the MIT Technology Review, and she has published in New York Times, New Yorker, Quanta, and so on. And she is also the author of 2 wonderful books, one about Coxeter, King of Infinite Space, and Genius at Play about John Conway. I would also like to thank Rolf Kaiser, who was a source for us. He knew Andreas Floer very well, and he has been a source for us to connect with people who weren't really on the mathematicians' radar screens. And we learned a lot about Floer, and as you will see, Floer was an extremely complex person. So let's start to set the stage what Atiyah thought about Floer. Some little issue. So here's what he said. The first time I met Grothendieck, I remember he was a whirlwind. He talked for hours non-stop. That was an experience never to be forgotten. Floer was on the other end of the spectrum. There were more reasons to forget. He was a quiet person, subdued. He didn't make a big impact. As for Floer's theory, I was keen to spread its impact around. It was Field's metal material, definitely. It was up to the Field standard. I did a lot of propaganda at conferences in those days. My role was trying to explain new developments of problems. People thought I kept bad company because I mixed with physicists. Physicists were too woolly. But Floer had spectacular new ideas that they could use and at just the right moment. He bridged the gap. He provided steep stepping stones between mathematics and physics. And mathematics comes in fits and starts. And here was a brand new idea that came from nowhere, or it seemed to, and opened a door to the future period of heightened activity. And that's rare. Donaldson, Floer, Witten, the ideas were inspired by each other. They opened the door and went out and explored all the wonderful new trees and flowers, Michael Atiyah. Yeah, as I said, Andreas was a very complex person. And it wasn't, I mean, he was special in some way, but you always only saw, depending who you are, two dimensions. You only knew he was somewhat complicated. And later, so what we figured out was that his life was actually organized in several parallel universes. For example, one was math, one was music, there were other ones. And he belonged to each such universe, but the other inhabitants, with few exceptions, didn't know about the other ones, the other universes and their inhabitants. So for example, in the music universe, a few had heard about Mikhail Gromov, Alan Weinstein, and Edward Zehnder. And there was a clear sign that Andreas cared about them. And even if he, I guess, it wasn't so clear for the people that he did. So I have here, okay. Now, this became quite apparent actually only on one day, namely on the day of his funeral. Actually, the people from these different universes came, and many of them didn't know. I mean, in the groups, they knew each other's, but for many of the people seemed to be strangers. So Fleur's work is in a rather short period of about 5 years. So here you see on the right-hand side in red, the submission dates, in blue when it appeared. And you see this is a rather short period. And this is not all of his work. And as you will see, he was actually at some point, starting from 1986, under a lot of stress. Now, here, for example, there are certain interesting things you see. This here is a propaganda article, Monopoles on Asymptotically Euclidean three manifolds, where he solved some conjectures of Cliff Taubes. So Cliff had tried that for a while and didn't succeed. And then Andreas solved them, and they were submitted. Now Andreas had some kind of his writing wasn't the greatest. So it makes quite a lot of sense to assume that the referees had a lot of complaints about it, but he never came to making the revisions. And this papers ultimately appeared only in the Floer Memorial volume. Now, the first group here is based on more classical ideas, and this part is in symplectic geometry. This is some other work on cubic Schrödinger equations with Alan Weinstein. And this part here is what he is famous for, Floer theory, Floer homology. This is a symplectic part here. This is a part connected with three manifolds. Then this is some joint work with Claude Viterbo and myself, where we use some of these ideas to study about the Weinstein conjecture, and I will say more about it. Now, there are a lot of posthumous publications, and they are all based on things of discussions and work which was done before his death. So for example, the first two publications, this was a little bit of a mopping up operation because, as I said, the writing wasn't the greatest. So one could say more and make it clear about the orientations part of in his work, transversality questions. And then this part here Ivar Ekland, who is actually in the audience, he invited us as as visiting professors to Paris in summer 1988. And just before that, Ivar Ekland and I introduced the notion of symplectic capacity, which was, of course, motivated by Gromov's non-squeezing result. But it has the important feature that it related symplectic rigidity question to Hamiltonian dynamics. So this had been done. It hadn't been, we were in the process of writing this down. And there was this program in symplectic geometry. Actually, I think the first program ever in the history of the Earth on symplectic geometry at the MSRI in August, September in 1988. And I was there in August and September 1988. And during this period, Floer was also there. He was at the university. We gave a series of lectures. So I talked about what is now called Ekland-Hofer capacities, and Floer about what we had discussed in Paris, namely how to get it from Floer theory. And there, his talk, he introduced the S1 equivariant Floer theory and showed how one can get the Ekland-Hofer capacities out of this. And we are fortunate that Alan Weinstein is a careful note taker, so he has a record of most of the talks which were given. And then I gave a talk about symplectic homology, but there the date was missing. And this led to this publications here, in particular symplectic homology, which is now an important tool in, for example, mirror symmetry and in many questions in symplectic geometry. So now, so this sort of sets the stage, and let's now look how this all happened. It starts in 1976, as far as if I have to take a starting point, and it starts with a paper by Jürgen Moser. So for the younger people, Jürgen Moser was sort of the Pope of dynamical systems of the time. He was a person of principle. He was a scholar. He had extreme knowledge, and he was very precise. So his work centered around what is called the action functional, S here, this display 1.5. And what you do is, just to give you an idea, you look at maps from the circle into R to N. And in R to N, you have the coordinates y1 to yn, x1 to x1 to xn, and y1 to yn. You integrate a particular expression over the loop. Lambda is a free parameter, and you get a function on the space of loops. And you can actually, the space of loops, you can equip it. It's a Hilbert space, so it has a smooth structure. You have a function on it, it's differentiable under Newton assumption on H. And you can, and lambda is an additional parameter. And if you see, if you differentiate with respect to lambda, then what you get is the equation H equal, if you look for critical points, H is equal to C. This is a prescription of the energy, and you actually get the Hamiltonian equation. So the critical points of these functions correspond to periodic orbits on a given energy surface. So here's what Moser thinks about it. However, this variational principle is very degenerate. For example, even the Legendre condition is violated, and is certainly not suitable for an existence proof. Now, as I said, Moser was a scholar with very broad knowledge, very precise. And in this case, he was actually wrong. So there's, of course, some message to take, particularly for the younger people, for example. It's good sometimes to question what your advisors say, or at least ask questions if they express certain opinions. So why did Moser say this? Now, what he said was based on state-of-the-art knowledge about so-called critical point theory, or otherwise known also as Morse theory. And let me paraphrase Moser. And what he says is that it's completely pointless to study this type of functionals because, and that is the underlying reason why he said this, is because the structure of critical points and the topology of the ambient space is completely unrelated. Let me paraphrase this again. What he said, there can never be a Floer theory. So let's try to understand a little bit what Morse theory or critical points theory is about. So you have, at least initially, you have a compact manifold, for example, this surface of a donut here, and you have a function on it. And it's not very difficult to show if you have a compact manifold because you can embed it into some large Rn, and you have a function on it. You can arrange that if you take, you can embed it in such a way that if you take a point on the embedded surface and read off the last coordinate, this is the value of the function, of the a priori given function. So you can always think it as being sitting in a space, and you read off one of the coordinates, say the last one. And then you fix you have the ambient metric, so you can express the function you have on that manifold by a vector field, and that's called the gradient. And you can study, for example, the negative gradient flow. Now, the critical points, for example, the maximum here and the minimum there, and there are some saddle points here, they correspond to zeros of this vector field. And if you pick this thing and you start your ordinary differential equation because it's rest point, nothing is going to happen. But if you take another point outside here, it will follow the gradient flow. And in fact, you can easily verify that the value of h goes down. And the only bad thing which can happen is it gets stuck, for example, at those critical points. Otherwise, it runs to the minimum. And so given a function on this thing, you can play around with the gradient flow, and you can move points up and down. And the only obstruction is, in fact, that they can get stuck at a critical point. So this is extremely good news if you want to explore this space by local properties of the surface. And in fact, if you have a manifold, you have a function on it, and let's assume that the critical points are non-degenerate, which means the Hessian is non-degenerate, it doesn't have zero in the spectrum, then you can define the so-called Morse index, which is the number of negative eigenvalues with multiplicity. And you can define this topological space here. These are all points where the energy, let's denote this function h, let's call it energy, is less or equals to d. And let's assume we have only one critical point on level d. You subtract this, that is m dot d. And then you have a topological pair, and you can take the exact homology sequence associated to this. And you get this long exact sequence. So algebraic topology is important in this context. And you can read off, if you know a little bit about the critical points, how the topology changes when you pass a critical point. In fact, since you have the gradient flow, if you deform levels down and there's no critical point in between, there will be no change. So the changes in topology always take place because of the critical points, and you can try to analyze this and can try to reconstruct the space from local information. Now, what was Moser's worry? Now, of course, this functional S is a functional on an infinite dimensional space. And the problem is, if you take the Hessian at a critical point, and here a critical point corresponds to an interesting thing, namely a periodic orbit for a Hamiltonian system on a given energy surface. So then, if the Morse index is so the number of eigenvalues for the Hessian, even if it's non-degenerate, there are infinitely many negative eigenvalues and infinitely many positive eigenvalues. And then terrible things can happen. Namely, it is known, and it's not too difficult to show, and one can use a shift operator to construct, to show something like this as a starting point, a shift operator, and do some mild construction on it, that if you take the closed unit ball in, which I denote by B bar, in a separable Hilbert space, and I denote by S, the unit sphere, then the unit sphere as a subset of the closed unit ball is a strong deformation retract, which means if you take the identity map at time 0, you can deform the identity map from the closed ball into a new map at time 1, where during the whole deformation, any point, any input point on S will never move. And at time 1, the image of the unit ball is in S. You can also show that S is contractible. Of course, something which doesn't happen in finite dimensions, and that is, of course, the reason that we have theories like homology theory. But this doesn't work in infinite dimensions. So what actually happens, algebraic topology goes up in flames here. And what you get is your short exact sequence, which you had before, just reduces to this. If you pass a critical point, there's no change of topology whatsoever. So what it means is there is no relationship between the structure of critical points and the topology of the ambient space. Now, Paul Rabinowitz was a student of Jürgen Moser, and I think he was in the lucky position, presumably not having been, at that point he was already a full professor at medicine, and presumably he didn't know what Moser had said. What he actually did in the period from 1978 to 1979 was he solved a problem which was actually much worse than what Moser was talking about. But this contribution, I will say a little bit more about this contribution, turns out to be extremely important. It shows, and Moser again plays a role in this, that you can actually study S. And this leads, his work from that period leads to the Weinstein conjecture, which is still a prominent conjecture in symplectic geometry, only solved in dimension 3. It leads to the initial breakthrough by Conley and Zehnder on the Arnold conjecture, because they were motivated by this breakthrough to study certain type of problems. It also led Frank Clark, who was working in optimization and this kind of things, to give, in certain cases, an alternative proof of one of the results in that period by Rabinowitz. And that leads to Eklund's Morse theory for convex Hamiltonian systems, which actually, I think it has been proved by now, is isomorphic in certain cases to a Floer theory. And his student, Viterbo, came up with what is called the Viterbo conjecture, I think very striking conjecture, which can be, one can try computers to derail it, but the computers so far didn't find a counterexample. And it is known by results of Ostrova and company that it applies a very old conjecture by Kurt Mahler about volumes of convex bodies. And you can read actually in Terry Towell's blog why it's so basically impossible to solve the Mahler conjecture. But if you solve the Viterbo conjecture, you get the Mahler conjecture. So what did he do? So what did Rabinowitz do? So he solves a wave equation problem. This is actually, so you have the wave equation operator, you perturb it by a nonlinear perturbation, which is time dependent, and you look for periodic solutions. It is a much worse functional than S, and he actually finds periodic orbits. Now, when Moser sees this, he understands that he's wrong, and he points Rabinowitz's attention to finite dimensional Hamiltonian systems. And this leads to the famous result by Rabinowitz on the existence of periodic orbits on star-shaped energy surfaces. Some further development of this where Alan Weinstein was the referee, and that led to the Weinstein conjecture. So this contribution is actually very important. It also leads then, as I just said, to the work by Eklund. And what is so interesting is that Eklund's theory for convex is based on a trick which you can play for convex things. But the interesting thing is convex is not really a symplectic notion. It's a usual, this is a usual notion of convexity. But we know that convex Hamiltonian systems have fantastic properties, but we still don't understand that concept. So what you would like to understand, for example, is if you're in R4 and you have a domain which bounds a ball, and you want to be able to run some tests and say there's a change of coordinates who makes this thing convex. We don't have an answer to that question, but that would, of course, mean if we would have such an answer, we would understand what the importance of convexity actually is. So let's go in 1982. There are two visitors at the Forschungsinstitut for Mathematical Research, the FIM, in Zurich. So this is Zehnder and Conley, and there's another one, John Moser, who spends his sabbatical there. Now, it's a few weeks before Christmas, and of course, this is a talk about Floer, so we haven't heard about him for a while. So let's keep these three guys in mind and look what Floer's up to. So Floer has just finished his undergraduate studies in Bochum, and well, he goes to Berkeley. So he starts as a graduate student in Berkeley in fall 1982. So he must have applied end of 1981, January of 1982 to be admitted there. And okay, so why did he go there? And one of his friends said, yes, Andreas wanted to, who grew up in Duisburg in the Ruhrgebiet. So Andreas wanted to see the world, and he wanted to go to a place with a lot of mathematical research. Let me also mention here that Andreas actually started studying in Aachen electrical engineering, and then he didn't like it, and he switched after a semester to physics. And then he decided he could study physics in Bochum, so he started in physics in Bochum, and then he switched to mathematics. So Andreas is a graduate student in Berkeley. So I asked Alan Weinstein, so Alan, who was his advisor at Berkeley? So Alan said, oh, he was working with Taubes. So Taubes actually had joined the Berkeley faculty in 1983, and then became Harvard faculty in 1985. So I asked Cliff. Well, Cliff Allen told me you were Floer's advisor, and of course I wanted to get some more ideas about Andreas. And Cliff said, oh, I thought he was working with Alan. Well, now this is what is called graduate student mentoring at Berkeley at its finest. It's a graduate student you never knew you had. Okay, on the more positive side, of course, it also tells us that Andreas was what is called in German pflegeleicht, easy to care for. Now, that Andreas is at that time in Berkeley, it will be really important because the MSI, just the Mathematical Science and Research Institute, just started. And it's the first program. It's organized, one of the organizers is Atiyah. Karen Uhlenbeck is the lead there. And in that first event, there's a first seminar. And that seminar is run by Karen Uhlenbeck and Michael Friedman. Here's a picture from 1973, so he looked a little bit older at that time. And it's about the work of Donaldson, namely Donaldson's work where he used Young-Mills equations to construct invariants for smooth four manifolds. So it turns out that Andreas is a participant. Dan Fried is a designated note taker for this seminar, and Karen Uhlenbeck remembers Floer gave one of the seminars and Dan and I had to fix up his proof. He wasn't on top of everything. So this, of course, is good news for the younger people. Even if you screw up, then if you think about it, get your act together, you can still become famous. So what does Floer learn there? So he learns bubbling off from the master. Karen Uhlenbeck, of course, in the initial paper with Sachs studied minimal spheres where the bubbling off occurs for the first time. Bubbling off is a breakdown of the analysis so that people even studied this kind of problems because it seemed hopeless, but she showed it's not hopeless. You can do certain things. Then she did bubbling off analysis in the case of Young-Mills, and these are the works for which she received the Abel Prize. Taubes' initial claim to fame is his gluing constructions for instantones. So he learns this. He learns about the Young-Mills equation. And Floer was sort of generally curious. He reads Witten's paper on supersymmetry and Morse theory, and he will be influenced in 1983 about what is happening at the FIM in 1982. Remember these three guys here. And his background from his diploma thesis is algebraic topology. In fact, his diploma thesis was concerned with Poincaré duality spaces, which are not necessarily, these are spaces for which you have Poincaré duality, but then don't need to be manifolds. They can have singularities and this kind of things. So now we will be saying more about Floer, and I want to sort of set the stage and give you some idea how he was as a mathematician, which in some sense also reflected at least some parts of his person. And I will read to you from the prologue with my book with Siobhan Roberts. And here it is. So we are embarking on this safari to explore the work of the German geometer Andreas Floer. One approach to mathematics, a path rarely if ever taken by Floer, is to imagine that you are standing in front of a big wall, the problem. And you have to get through the wall by any means necessary. Maybe a sledgehammer will work. More likely, however, you need some heavy artillery. Some heavy artillery will be necessary. But really, it's you against the wall. You run up against it, you run and run and run. The wall never moves. If you're powerful enough, gradually you might create a crack. You run against it some more. The crack gets bigger. Eventually, you might get through. That's a success story. Your head hurts, but the adrenaline overrides the pain. Another strategy, Floer's preferred path, is to imagine you are an anthropologist in a mathematical jungle. Understanding the mathematics, the creatures under investigation is like exploring the jungle's wildlife and vegetation. Out on a fieldwork expedition, you set off every morning from camp with your machete and clear encroaching brush and dangling vines as you go. You're working away, moving forward. Sometimes it's a slog and you spend too much time following a boring, seemingly trivial tributary, or worse, you get mired in mud. Other times you happen upon lush valleys and wide vistas. Maybe you cross a ditch, an hour later you cross another ditch, and after crossing a bunch of ditches, you realize that all these ditches are part of a huge pattern that some ancient civilization dug into the earth, like the Nazca lines. Unlike the problem-oriented approach in the jungle, you are not fixated on any one creature. Instead of running against the wall, you veer to the right and wander left through woods. And around the corner, there you find a door unlocked. It opens onto the same place, the other side of the wall. Not only have you achieved what you wanted and arrived at your desired destination, but you have also learned about lots of unexpected creatures along the way. Welcome to the Floer jungle. And so it describes somewhat how Floer was thinking about it, but it's somewhat of an idealized situation. I think that would be Floer in the steady state. But Fleur's contributions were in a very short time, and as we will see, he had a lot of stress. So I had sort of peel away the stress because he was sort of put in a situation where he couldn't live precisely how he would like to do things. But I think that would capture it quite well, how he thought about this kind of the way to do mathematics. And I think that was, in fact, the way to do it, which was the best way for him to work. And I think for the younger people here, I think you have to figure out what is the best way to work, and then you maximize your abilities by just choosing the right approach. Okay, now we go to Russia. So in the 60s, Vladimir Arnold made a remarkable conjecture. So let me say something about Arnold. So Arnold was a quite remarkable character, somewhat of a daredevil. He liked to make strong statements to see the reaction of people. And unfortunately, he died in 2010, and it wasn't necessary. He actually could probably be still alive if he would have decided to go to a hospital, but he decided to be a tough guy, and that wasn't a good idea. Actually, before, there were several occasions where he also almost died, once he tried to swim across the Bay Bridge in San Francisco, that is where the Golden Gate Bridge is. It would have been a good idea to ask the locals, because if the tide goes out, you end up several miles outside and you drown. So he didn't manage to get through this current and was always repelled, and he was complaining about it. Actually, that saved his life. And then he tried to learn the Eskimo roll and got stuck with his head in mud and so on. So he definitely pushed the limits in life and mathematically. So here's a remarkable conjecture. You can find it in one of the appendices in his book on classical mechanics. It's formulated as a theorem. Every symplectic diffeomorphism of a compact symplectic manifold homologous to the identity has at least as many fixed points as the smooth functions on this manifold has critical points, at least if this diffeomorphism is not too far from the identity. Actually, it turns out if this diffeomorphism is not too far from the identity, it's almost a triviality. And if you don't know this, nobody had an idea, then it's actually a conjecture. And there are versions of this for the two toroids at other places. So there are different versions published at the same time. Now in 1978, Eliashberg, he was living in the former Soviet Union, and he was considered by the Soviet system as a suspect character. So he didn't really have a great time there. In particular, if he would send mail out from Soviet Union to other places, it presumably wouldn't get there and so on. So he thinks he has a proof of the Arnold conjecture in the case of surfaces in 1978. And before the paper was complete, he gives the following happened, that Anatole Katok, he was allowed to leave Russia. Anatole Katok was living in Russia, but he was also American citizen.
Yeah.
So, somebody should switch off his microphone. So Anatole Katok was American citizen, and that was for some reasons related to World War II, and he was allowed to leave. And Eliashberg took this opportunity and gave him the not completed draft to deliver to Mikhail Gromov. And it turns out that the preliminary version actually had a gap, and Eliashberg, when he was continuing, realized that there was a gap, but he managed to get by some way the second draft also to Gromov. So now Gromov was sitting on two papers, and he gave one of them to a group of French mathematicians who get stuck. So so the conjecture is that he gave the wrong paper to them. And I actually, about 10 years ago, so Gromov also had a part-time appointment at Courant. I asked him this, and he thought, well, yeah, there was definitely the possibility that he forwarded the draft with a gap to the French mathematicians who ran the seminar about it. And here are some of the members of this group. In fact, it was the topology group at Orsay. Francois Lodenbach is in the audience, and he told me that they had this tradition, and the topology group was, the definition was very broad. And if there was something interesting happening with some topological flavor, they ran seminars on it. And so they get stuck. And in 1982, remember John Mather was at the FIM on his sabbatical. He visits his friend Michel Hermann. Michel Hermann, extremely distinguished dynamical systems person. And Michel Hermann tells him about the failed attempt. So John Mather returns to Zurich, and Conley and Zehnder tell him what they are doing. And Mather tells him, oh, well, with this methods, you should be able to solve the Arnold conjecture for the two toroids. And in fact, they succeed. And within a few days, they actually do it also for higher dimensional tori. And a few weeks later, Zehnder gives a colloquium at the University of Zurich. The news travels to Paris, and the attempts to understand Eliashberg's paper cease. So let's go back to Andreas Floer. So Floer spends the summers of 1983 and 1984 in Bochum in order to do his Ersatzdienst. So at that time, you had to do military service, but you could replace it under certain conditions by social service, which also could be stretched. I think which in total was longer, but it could be stretched out over longer periods. And he did these surveys during the summers. So at the latest, then he learns in 1983 from Zehnder directly about their work, and he starts working on the surface case of the Arnold conjecture. And that was, of course, a natural thing to do. And he succeeds and shelves this material away and attempts more general cases. And that is where he gets stuck. So we are now at the beginning of summer 1984. And I think when we look back and see what people knew before Gromov and later, and how could we even, with that knowledge, improve what was known before Gromov and extend ideas, I would say it's not very likely. So I would maintain, but of course, after telling you the Moser story, I have to be careful. So I think that basically the only way, the easiest way to get unstuck is actually by modifying Gromov's methods, coming from the pseudoholomorphic curve theory, which you view as a technological advance and adapt it to the work when you want to think about the Arnold conjectures. So the paper by Gromov is submitted to Inventions in 1985. Eliashberg told me that he got a preprint in October of 1984. And when Gromov submits it to Inventions, that's the time when there's a paper floating around for the general public. So since it wasn't around yet, it's something like waiting for Godot. Floer is stuck. So then something happens. Floer quits Berkeley and obtains his PhD in Bochum in December 1984 with a previously shelved away material on surfaces, and then he goes back to Berkeley. So I never asked Floer about it. I should have, but I had a discussion with this about Abbas-Bari. I don't know, remember why that discussion happened. And Abbas-Bari, Floer and I, we knew each other from 1983, and and it turns out that Bari met Floer somewhere. He was at that time at the University of Chicago, and told him that I can prove the Arnold conjecture in general. So now it was true, I could prove an Arnold conjecture, but it was a different one. And Floer, that's my interpretation, panicked and took this shelved away material and turned it into a PhD. In fact, I was at that time working on the Arnold conjecture about embedding a compact manifold into its cotangent bundle as an exact Lagrangian embedding, following Chaperon, who is also in the audience. He, after Conley and Zehnder did the result, Marc Chaperon proved this for tori, and I did that for general manifolds. But then shortly afterwards, or maybe simultaneously, even Lodenbach and Sikurov approached the same problem by different methods, which was much easier, and their paper is much shorter than mine. But that is at least my explanation why Floer switched for a short time to Bochum. So then Floer actually goes back, and it seems to be that he continues as a graduate student in Berkeley. I think it was for him the most convenient way to do mathematics. And let's see what he knows at that time. So in January 1985, so he has this algebraic topology background. He understands bubbling off, gluing, Young-Mills equation. He understands the Conley-Zehnder paper, has actually generalized this to surfaces. He knows Witten's paper on supersymmetry and Morse theory. And then in the preprint of Gromov comes out, arrives in Berkeley, and Alan Weinstein runs a paper on this Gromov paper, and other speakers are Floer, Tom Mofka, and Julien Tang. And in June 1985, according to Taubes, and he says he remembers it very well because he was just packing his stuff to move to Harvard, Floer visits him in his office in Berkeley and says something along the lines, I can do infinite dimensional Morse theory. Also, according to Taubes, he wasn't too impressed at the time, but he says this is quite common for him. Taubes has some kind of an interesting humor. He says, if you would get a dime for each time, one dime for each occasion, where somebody told him something where he should have been impressed and wasn't, he would be a rich man. So in my interpretation, it means that Andreas Floer has an idea in the direction of the Arnold conjecture in more general cases. So in 1985, he starts as a postdoc and instructor at Stony Brook, and he has a plan and he's working on it. And it's a bold idea to bring all these things together. And again, because of the Ersatzdienst, he goes for the summer of 1986 to Germany. And he goes to Bonn, where the Arbeitstagung takes place. And that seems to be the first time he gives a lecture on what will become Floer theory, but they didn't do recordings. But shortly after this, he gives a talk at Stony Brook on this. And I think that's the first recorded talk. And if you go on the internet, you actually can find a link to this. It was a talk in Sullivan's seminar, and he started very early to videotape the talks in his seminar. And now here at the Arbeitstagung, this is probably for the first time that Atiyah and Floer meet. And here is the program, and you see some of the usual suspects. And also you see here that Fukaya was, before he became a symplectic geometer, he was working in Riemann geometry. He was giving a talk there, and then he went through a phase transition, started in symplectic geometry, and invented things like the Fukaya category, which is important in mirror symmetry. So now, so Andreas actually told me about this. I said, how did you manage to give a talk there? He said, well, he went there, then he approached Atiyah. He told him that he can do the Arnold conjecture. Atiyah got excited about it and also suggested to him he should work on the Chern-Simons functional. So Atiyah was really excited about this stuff. And Atiyah was, of course, a fantastic mathematician, but his abilities in propaganda were on the same level. So Atiyah then was running around on the planet and telling all the wonderful things Andreas Floer did. And the result of this, Andreas got a lot of preprint requests at that time. Of course, the internet didn't exist on the level it existed now. So Andreas always gets his preprint requests, and basically nothing is written down at that point. So that was part of the situation which increased the pressure on him. And when he went into this Arbeitstagung, I'm sure he felt under pressure, but it was for the purely symplectic things. And Atiyah gave him some more homework to do, which then leads to the work on three manifolds using the Chern-Simons functional to define the Floer homology there. So let's have a look on the timeline of the mathematic development when we want to end up at the Floer, from the Floer perspective. So in the 30s, Morse develops the Morse theory using gradient flow and algebraic topology to work on finite dimensional manifolds, say preferably compact manifolds. Then in the 60s, Palais and Smale extend this to infinite dimensions. You need some compactness, that what is in that case now called the Palais-Smale condition. And you need finite Morse indices. And then you can generalize to infinite dimension. And the finite Morse indices is really important because then you still have a relationship between the nature of the critical points and the ambient topology of the spaces. Now, Rabinowitz uses the Palais-Smale condition and uses that the functional S has something in addition going for it. Namely, there's some kind of Fredholm structure for the gradient flow in the background. In some sense, you can view the gradient flow as an infinite dimensional flow, which is rather trivial, times a meaningful finite dimensional flow. But the infinite dimensional flow completely spoils the topology. But if you can peel this away and this Fredholm structure sort of allows it, there's meaningful information there. But Rabinowitz's method actually runs into very serious technical limitations. Then what was also important, then Witten rediscovers what was known in his paper, was known to Milner and Thom, but never received a lot of attention, namely that in Morse theory, if you are not interested in the homotopy type, but just in homological invariance, it's enough to study gradient flow lines between Morse index difference 1 critical points and Morse index difference 2 critical points. And of course, Conley-Zehnder theorem shows you that you can use, sends a signal to Floer that you can use this new technologies to, in nonlinear analysis, to approach problems in symplectic geometry. So then, from the Floer perspective, the advance of technology, Gromov's paper can be viewed as an advance of technology which can be modified more. And then what Floer says is, so by what I just said is you don't need the gradient flow, you only need the gradient flow for studying critical point, Morse flow lines between critical points of difference, Morse index difference 1 and 2. And then Floer says to himself, well, maybe instead of having this flow thing, I need some flow-like things, which can be obtained by solutions of partial differential equations with enough compactness properties and other suitable properties. In particular, it should be possible, the structures you need should allow you to say what the difference of two infinite Morse indices is. And in fact, what comes out is that the difference of two Morse indices doesn't need to be an integer, it needs to be a cyclic number or something. So there's a lot of new possibilities arising there. And the Floer ideas generalize these things and have been further developed, and many, many more things can be done. And here is sort of the idea. So you consider this pictures of broken flow lines, and the Morse index difference is always 1. And then Taub's gluing, but of course in this case easier situation, say that is in the generic case nearby a flow line of this kind, in fact a family of flow lines. And you can parameterize these families. It's a one-dimensional manifold with boundary, has to go somewhere, and there has to be another broken line. And you can then get algebraic relations out of all these pictures, and you can use this, if you have some orientations, depending on which coefficients field you choose, to construct a homology theory, which in the classical case would actually be singular homology. But since you now study PDEs, you have many, many more possibilities. And here, this could be a 4 broken flow line in a more complicated situation where these are Riemann surfaces. And this opened up the door to fantastic developments in symplectic geometry, but also in dynamical systems. It created a new field. One had the tools to create a new field like symplectic dynamics. Now, how was the reception of Floer's idea, particularly before the ideas were in written form? I have to say they were mixed. Of course, Atiyah loved it. I think for Atiyah, things like beauty and so played a role. So I'm sure Atiyah didn't went into the technical details, but he decided these ideas were too good and had to be true. I mean, they were so good they couldn't be false. But this was not the general picture. So let me explain a little bit what Gromov thought about it. So if you read in the I think it's the notices of the AMS, his response to receiving in 1997 the Steele Prize for his pseudoholomorphic curve paper, you find the following. Floer has Morsified them by breaking the symmetry, and I still cannot forgive him for this. Alas, prejudice does not pay in science. Somewhat mysterious sentence here. And then he continues, Macduff started the systematic hand for them, which goes on to present day, and what goes on today goes beyond these lines and the pen behind them. And of course, we should mention Dusa Macduff here, because she took the geometric side and then she ran and she actually formed and directed the agenda from the early days on about a lot of the geometric applications in symplectic geometry. So, but let's go back to, and Dusa is also in the audience. So let's go a little bit and try to understand what Gromov said here. So here's my explanation for this. In 1986, there was a conference in Il Chioco, NATO conference. So there's no military underlying thing. NATO had also a cultural, the NATO contract also had a cultural part. And one of the organizers is Paul Rabinowitz. And the theme of this was that the nonlinear analysis now had been used in symplectic geometry. Gromov had done his things, bringing these people together and exchanging ideas. And Floer was invited, but I think he was applying for a visa to start as an instructor at Courant. And so he could not come to, I think he was in the US, but he could not come to this conference. But he had explained to Zehnder, when he was visiting Germany for his Ersatzdienst, he had explained him these ideas, which he then also presented in the Arbeitstagung. And so Zehnder, who is actually today in the audience, explained this. And Gromov is in the audience, and Gromov thinks it's deeply flawed. So there's actually a memorable discussion going on. And I think what happened was the following. Of course, Gromov understood pseudoholomorphic curves extremely well. And he knew that you, in order to be able to handle this and the bubbling off phenomenon, you needed control of the area and the whole of the area of a holomorphic curve. And the whole theory is designed in such a way that the area is controlled by topological invariance. Now, if you do if you do the theory of one complex variables, you know the notion of a pole and you know the notion of an essential singularity. And you can actually bring the study of poles into a context where you actually have area controls, but in the case of essential singularities, there is no area control. So I think he has this in his mind because Floer is studying Riemann surfaces which are non-compact, for example, cylinders. So you have these infinities, and the infinity, of course, and in his approach, there is no visible area. So I think what Gromov thought that there's no control at the end of the pseudoholomorphic curves Floer starts. Of course, Floer doesn't study precisely pseudoholomorphic curves. He perturbs, he breaks the symmetry and takes which looks like a lower order term and therefore insignificant. But this lower order term plays an important role. It turns this problem on an unbounded domain into a Fredholm problem. So even if it's lower order, it is actually a significant part. And there is an underlying variation of structure. And this actually gives you a different energy to control, which is not area, but something else. And I think since there was nothing written down, Zehnder explained it from his view of point, which took basically this variation problem for granted, and Gromov saw it from a different angle, and there was a complete mismatch. But of course, shortly after this, Gromov understood the depths of Floer's contribution. And it seems that I did some work to do the Listonic-Schneermann theory, where I bypassed Floer's homology theory. And actually, I did the Listonic-Schneermann earlier than him by taking Gromov's ideas and modifying them. And Gromov knew about that paper. And then you could, and it was really in the framework then of where you could do Floer theory, and but obtained from his ideas. And I think that might have played a role to change his mind. So I think we are now at the end. And I, in particular, would like to encourage the young people to ask questions. So there are a number of the old timers in the audience. And we can say a lot about, of course, Floer, but also about the development of the field. And one of the wonderful things of symplectic geometry was that it was created by people in different mathematical disciplines, which just changed what they were doing and bringing the culture of the different fields into this. And it is actually one of the really friendly fields with all kinds of different characters and a different culture, which just formed this field. And I think the elders in this field sort of set the tone, and it has developed as an extremely friendly field. Okay, so thank you very much for your for listening, and I'll stop sharing now, and you can ask questions.
Yeah, thank you, Helmut, very much for this historically and mathematically very rich talk. And as you said at the beginning, we take something like half an hour to take questions and answers and try. And I think we should use the chat possibly, right? And then we try to help each other that you get all the answers, so questions, so to say.
Okay, so let me see. I see just that Karen Uhlenbeck is there. So Karen, please don't run away, because I'm sure you have interesting things to say depending on the questions which are being asked.
Yeah. Okay, so now we're open for questions, and maybe comments also are very welcome. So maybe somebody breaks the ice, so to say. I mean, if somebody wants to speak up, then just go ahead.
Karen wants to say something, but Karen wants to say, but go I don't hear. Karen. We don't hear her. Karen, we don't hear you.
I've got my hand.
Now
Is that better?
Oh, yeah, that's very good.
Yeah.
Hi, Karen.
Hi. That was a really interesting talk. We don't hear things like that often enough. I mean, it's amazing how the landscape changed in such a short time. And I also remember Atiyah. I think I learned about Floer's ideas from Atiyah. And, you know, I immediately understood it. And I thought the technical difficulties were too great. I mean, this is the, you know, I was the one who discovered these some of this bubbling off phenomena, and you know, my head always stayed on the fact that it was really hard. And in the historical developments, the next generation came along, and they just took it for granted. And so that's a comment on why us old people, I mean, our established people don't always have the right view of these things. Anyway, it was an excellent talk, and he certainly was a complex person. And I think it's interesting to notice how these big-eyed changes come, and they come from outside, not inside. And this is very striking to me. So this is a comment to younger people, because if you just follow the leaders, you don't really get anywhere big. Anyway, thanks for listening. And I do appreciate the talk. I wish we had more of them.
Thank you, Karen. Karen, you're my hero. So the next one.
Well, I would like to say something about Floer and Stony Brook, because I remember when you gave this talk before I heard it, and you asked me, what do I remember of Floer and Stony Brook, which was in '85, I think. And not much, because I wasn't, you know, I was very occupied with Thomas and sort of, I didn't know anything about this more dynamical approach to, I was interested in the geometric side of and J-holomorphic, closed J-holomorphic curves rather than other things. But I do remember him saying, I mean, I went to some of his talks, and I also remember him saying, you know, that all the people want to hear about the three manifold things, and he's got to do the symplectic geometry things, and sort of cope with all the technical difficulties that he had to write down. And I want to say, I remember I have some old notes of his, which I should give you, Helmut, so that you
please.
That you could look at them, because I learnt a lot from him. I mean, when we were at the MSRI, that program, he was the one who explained to me some analysis. I mean, I knew no analysis. I was very ignorant, and I didn't know any of this Fredholm theory. And I remember Misha saying, "Oh, this is, not liking this, what I think he thought of as a Germanic approach." I've always thought of it as a Germanic approach.
I just see that Misha is there. So
yeah, I know. All these
I want to know if I was right.
It doesn't sound like me. Yeah, I had some other reservation, but I had geometric reservation.
Oh.
And what I was worried for, there is a problem, which is no. And I got a universal symmetric kind of solution which you couldn't work. And Floer, the key idea was to break symmetry, and then it works. And this I couldn't accept, because I need like breaking the symmetry. Not about Fredholm or this, what you say, essential singularity. I would accept anything. I didn't like breaking symmetry. And I still don't like it, I must say. Yeah, because it's symmetric thing, you beautifully break it, it's a disaster. Well,
I do remember reading your first paper, Misha, and on J-holomorphic curves, and you did all the analytical thing completely differently. It was done from a very different point of view. But there are obviously different ways to prove the same kind of estimates of what you need.
No, yeah, you did it just simply, I didn't need all this machinery. I did exactly what was needed.
Mm-hmm.
Yeah, but definitely interesting times.
Alan Weinstein was at the IHS, and he immediately said, well, you have to use them as gradient line for the Morse theory. It was immediate reaction, Weinstein. And I didn't appreciate it. I said, well, okay, so who cares? This was a very good remark, which I should have taken. And also I can say that geometrically, you could recapture Arnold conjecture mod 2. You don't need Floer theory just by because by looking at this, but again, I didn't like it. It was sort of very special. And Floer actually suggested that we write joint paper, but I kind of didn't understand what he was saying, and thought, well, it's kind of not a good idea. And I didn't accept it, which was probably a mistake.
Well, I remember,
because he believed I understood it, but I didn't.
Floer gave these talks, and from my point of view, they were terribly technical and formal. I mean, but with lots and lots of definitions. So it was hard to sort of understand the big picture. So I always find them rather overwhelming. Though I heard them, but they were not. It was not what I was really interested in at that time.
Well, further questions, comments, please go ahead.
Mark, I remember, I think due to Floer, or maybe you with him, that he didn't care if this what he was doing was to have applications or not, but just because for the heck of it, he wanted to do that. He had this regardless of his next stage. This, I think, is an essential point. And this is a very kind of it's attitude good for some people. It's not very good for everybody.
No, right. I think for the younger people, you have to look at what you are good at, and then you just find the right mode, how you operate. I mean, in this prologue, which we described, the two extremes, the problem solvers who actually like to run against concrete because it creates a lot of pain, and then when they are so powerful enough to get through, there's headache, adrenaline, everything flowing, and they're happy about it. And there are others who just explore, and there's a whole range of things in between to do. And the disasters happen if somebody has the ability to do one, but tries to do precisely the other. And you see sometimes that, for example, students of famous people try to be copies of these famous people, but they should be actually doing rather something different. and that can end up in unhappy people. So
again, you're citing thing by looking at how different people function. Every time there are different approaches lead success, you don't know what will be the next time. So he was certainly speaking about physicists and how they arrived at their theories.
Misha in outer space now.
Yeah, now the connection broke, so to say. So just look in the list, and there's no hands up. Oh, there's some things in the comment, yeah, in the chat. So
Eva, you want to say something? But you have to unmute yourself.
Well, I was just wondering, in the same period, you had very active things in celestial mechanics. Huge progress was done, also work by Marshall and so on. And of course, these are very standard Hamiltonian systems, but there was never any connection between those two.
Oh, this has changed. This has actually changed.
So I'm happy to.
Yeah, so we actually had this conference over Wolfach, and there were talks about it. And these pseudoholomorphic curves now are being used in celestial mechanics, where you can construct surfaces of sections by global methods, for example. And before, for example, Poincaré constructed them in a particular case, and then they persisted under perturbations. But now one can use pseudoholomorphic curves to do things in general. And in particular, there's work on by Agustin Moreno and Otto van Kurt recently in using this series. And I also, there's somebody who should be muted and isn't. So, and in fact, for example, Urs Frauenfelder wrote a book, and Otto van Kurt wrote a book about using pseudoholomorphic curve series in celestial mechanics. And they also worked with somebody with NASA connections, and they found some interesting orbits by predicting them using Floer theory, that there had to be some interesting orbits between the Earth and the Moon, where you can start
there is a problem
where you don't want to put the space station at the Lagrange point. You want to put it, for example, on an orbit which goes up and down in the three-body problem, because on the poles of the Moon you have ice, what they know, and ice is always good to have. Now you can turn it into rocket fuel. Here, liquid hydrogen is a fantastic rocket fuel, and so but you want to use it as a gateway for space exploration. And there were actually, by this person involved, presentations of this to ESA and NASA, and then they make feasibility studies, because building a spacecraft and a space mission is not only the mathematics. Like if you make a slingshot around the Earth and you stay only 3,000 kilometers away from the center of the Earth, you are dead. Yeah, so there are engineering challenges, how you have to do certain things. And so this kind of methods actually went so far that they sort of start percolating actually probably into applications.
So Helmut, there's a question from David Beccara. So many knew him, Floer, as a student and collaborator during this story. Did anyone had him as an advisor figure?
Yes, Edward Zehnder. Edward Zehnder was, so he got the PhD with Edward Zehnder, and Eddie talked a lot with him. So Eddie, if you unmute yourself. So while Eddie is unmuting himself, so I only met Floer in 1983. So Floer had definitely a closer relationship with Zehnder, but the definition of close relationship for Andreas was a very particular one.
So and, now it will work. No, now it got closed again. And
yeah, so in 1983, there was a conference organized by Felix Browder on nonlinear analysis in Berkeley, when Floer was already a graduate student there. And Zehnder introduced me to him. So at that point, I was a lecturer at the University of Bath. And Abbas Bari he also met him there for the first time, and we actually went out quite often for dinner and drinking some beer, and we talked about mathematics and so on.
So I think now,
Eddie, you can be heard now.
Yeah, but you don't hear me.
Oh, we
Yep,
do. We do.
We hear you now. Perfect.
Ah, well, Floer appeared at my door in Bochum and asked me, do you have an interesting topic for my thesis? And I didn't know him. He didn't introduce himself. I never saw him in any of my lectures, so I asked him in and explained him our proof of the Arnold conjecture on the torus. And he got more and more agitated, found it very interesting. I told him our main idea was to look, instead of fixed points or critical points of the functional, you should look at the set, at the structure of the set of bounded solutions of the flow. And of course, we could do that easily because we could put it down to finite dimensions and used several things. In particular, we could homotop the problem there and so on. And I told him he should start, if he's interested, with the Arnold conjecture for surfaces. And that's what he did in about 3 months. And then I told him he should really go to the general case, looking again at the bounded solutions of the not regularized problem. And that's what he did. He came up, you need compactness, and then you look at the flow lines. They're called now Floer lines. These are just the flow lines of the gradient flow in the degenerate case, where you don't use a lot of analysis. You just write down formally what the flow line is and study the structures. And then he used an idea of Conley, how to homotop the problem into another one, keeping the algebra fixed, and you homotop it up to the point where you get only the flow lines of the function on the object you have. That was the standard Morse theory on the manifold itself, and that's how he solved the problem in the general case. He always came to my office and we talked about his ideas. At first I didn't understand anything, but as time went on, he got better and better in his explanations, and I pushed him very hard to write down things. He had a hard time to write up things. He would come to my office when he completed his thesis. He would already scream outside of my office that I would turn him apart whenever he entered, and that's what I actually did. But in the end, he really learned how to write things with loving care so that people would understand his ideas. The private person I never got to know. He was sort of making a difference between grown-up people and younger people. And I belonged into the field of grown-ups. He stayed away.
Thank you. Helmut, there's another message in the chat from Semen Retchikov. Maybe Semen Retchikov himself or herself can just speak up and ask the question.
Oh yeah, thank you. It's an amazing talk, by the way. I wish these talks are so rare. They're really inspiring and enlightening. So it seems, based on all the comments that all of you guys made, that there's like a lot of people had the thought that, okay, we should be using, the J-holomorphic curve equation to do Morse theory. Kind of Weinstein, Hofer kind of all had, this is sort of a little bit in the air. But so somehow Floer was the one who really did this. So was it that there was like, people were, it was an idea, but people were unsure how to really make it work? Or there was like a lot of skepticism? Or was it that sort of, Floer had this kind of vision of how you should structure these things, and then nobody wanted to try to do that because it sounded too complicated? What was this sort of, there must have been this very complicated period when, it was possible, but no one really went for it.
Yes, so I can actually tell you. So I gave in January 1984, I gave a talk in Paris, and I talked about the embedding, about the solution of this Arnold conjecture of the embedding of compact manifold into its cotangent bundle. And that is when Sykorov was in the audience, and Lodenbach were also working on this thing. And Sykorov, I think, gave me a copy of Gromov's preprint, which I was looking at on the way back from Paris to Bath, where I was at the same time. And the knowledge I had I knew Rabinowitz work very well. Yeah, it crossed my mind there as well that one should just write down this unregularized PDE. Okay, so, but then of course you have to do it. So in 1984, then I was moving to the States and so on. And it turns out that I had thought about it, but I didn't do it because it looked like a fantastic amount of work. And you have to start, I mean, the ingredients are also not lying around there. I mean, it's a multi-year project. So I have a family, kids, I have to pack, move to the United States and so on. So I'm settled then in 1986, I have to look, 1986 or 1987. That is when Floer writes his first paper in the symplectic context on the unregularized gradient flow. I'm actually the referee. I said, oh yeah, that is what it clicks, yeah, this is how it should be. And then I can just sit down, and I had a different focus than Floer. So I wrote the Lusternik-Schnirelmann theory. This was, he did the analysis, which I would have done to do, and he used the Gromov idea as a technological advance. And that was also in some sense my viewpoint. And he did sort of the dirty work. I was the referee, but there's the things you immediately understand. It's the technical things. And then I wrote this Lusternik-Schnirelmann proof, which was actually published earlier than his Lusternik-Schnirelmann proof, because he first had to do Floer homology, and then he got from Floer homology to Lusternik-Schnirelmann, but you could just shortcut it. And this thing, I think, my paper Gromov saw, and it starts sort of really doing his ideas and doing more deformations and getting to this. So I think, so at some point, also Abbas Bari told me that he discussed this Gromov my proof. So so that must have been in '84 or something like this. So that I don't know, but that perhaps played a role. I don't know. We can ask Misha. So this is a speculation. But yeah. So, but he was, of course, in a good position because he had all these people around when he was in Berkeley who had thought about certain aspects in some wider context, which you could bring into things. But it's still a fantastic amount of work he has to do. Yeah? I mean, even the symplectic part. And then Atiyah tells him, well, you should also do 3 manifolds. And he puts some more stuff on his plate. Then Atiyah runs around, does the propaganda, and Floer on a daily basis gets preprint requests. Yeah? And nothing is written down. Yeah? It's pretty stressful.
I think we can take the next question also. We still have a couple of minutes. So Helmut, there's Michael asking a question. Maybe Michael also could speak up himself and just ask the question, or otherwise I read it. Michael? Okay, then maybe I just read it. Do we have any idea what Floer would have studied or come up with had he lived longer?
So, well, that's a good question. So let me first say that I think there's no doubt. So so let me first say a little bit more about this. So Floer was a Fields Medal candidate for 1990, but he was pushed clearly by Atiyah, and there were Vaughan Jones and at least that is what I think, Vaughan Jones and Witten, and then he had to sort of sacrifice a pawn, which was Floer, because he would have another shot in 94. And I'm pretty sure at that point, Floer would have gotten the Fields Medal. So in 1990, I definitely know that Floer was studying things like cyclic homology on the side. Okay. So he had some interest in this. So he was just generally interested and developed his views on certain things, and then he stored it away, or he hooked it up with other things he knew. And then I think if then some picture emerged, he wrote it down. I think that was his mode. So I think it would be too stochastic to believe what he would be doing now. I think he was just looking what is interesting, and he wants to know about it, and then he hooks it up with what he knows and maybe has a completely different take on it. So it's hard to know. I mean, it's of course a shame. I mean, he was such a talented guy. And I think he will definitely be one of the German mathematicians to be remembered for a very long time. I mean, there was really a phase transition happening.
Thank you. So I see not any questions for the moment, and maybe by what we have planned, so to say, 1 hour talk and a half hour, so to say, formal discussion, if for one, it's maybe good to make a break here and thank all the participants and thank Helmut once again for this really fantastic and very, very rich talk. And we just agreed that here the official part, so to say, ends. So to say, and then Helmut is open to stay online and continue some informal further discussion. That's okay,
yes, so,
right?
Sure. Whoever wants to do something else, prove a new theorem, can leave now. If you don't want to leave and stay around, and you can ask some questions. And I think Siobhan Roberts is still around. She actually interviewed a lot of people about Floer, and yeah, so of course we'll not give everything away, but I think we have a pretty good picture about Floer as a person in his different universes, and we have very good ideas about what other mathematicians thought about him and their view, and yeah, so there's a definitely very complex picture about Floer. Yes, so feel comfortable and ask questions. What about Felix Schlenk, one of the daring characters?
I can ask a question if you need. So you mentioned
Sure.
this. You mentioned that Floer gave lectures about S1 equivalent Floer homology, and then of course nowadays we have such theories. But are there notes? Are these Weinstein notes?
Oh yeah.
available?
Oh yes.
Ah.
I can send you a copy. So the Weinstein notes are me giving. So there are 4 talks. So I give 2 lectures about symplectic capacities. In fact, the semester before, Ekland visited me and we invented what is called now Ekland Hofer capacities. And then Floer in '86 started at Courant, and Vitor Bo was there. So it was a pretty good time, and we worked together on certain things, and I had a lot of discussions with Floer. Then in particular, we started discussing in Paris about, so we always refer to our personal chairs in the Jardin Luxembourg. So it was summer, there were these things you could lay down, and we were laying down and discussing mathematics. And Ivar Ekland was a host, but he wasn't very demanding. So we had a lot of time for ourselves, and he invited us frequently for dinner. So we had a very good time there. And there, yeah, so then what came out of this is that you do Floer theory in R2N. You multiply by the classifying space, so everything is in there, and you can get the Eckland Hofer capacities out of there. So this was given as a talk in 1988, and then I gave a talk after this about how to do what's called now symplectic homology. And then there's a year later, there was a Durham conference, and the proceedings is sort of an outline of this. So published in 1989 or 1988 or something like this. So, but I can send you the notes. Yeah.
So Karen would like to ask a question.
Right, I had my say, but I can't resist saying, I want to say something about that wall. My experience over decades of mathematics is never bang your head against a wall. Look for another wall that has a crack in it. That's, I mean, the description of banging your head against the wall as a way to do mathematics is completely wrong to me.
Yeah, but yeah, I understand. So there are different people. So for example, I was a guy running against the wall, and the head hurts, and I get through this and had some success like this. Of course, then I also have a family. So, you know, you come home, the kids want to talk to you, and you just were banging your head the whole day, and it's still present there. So you're not a good father, I must say. That was a message we took from this. And then I was talking to Floer and observing him, and Floer had sort of this different attitude. So I remember once I met him in New York. We're doing math, and you know I have to travel there for 90 minutes and 90 minutes back from Rutgers. So then it's 5 o'clock, and he said, then I say, well, we should also discuss this thing. And then he looks and says, it's 5 o'clock. Courant only pays me to do mathematics from 9 till 5. And then he went. So and so there were this kind of occasions, and yeah, he was of course in stress, but he had sort of this different viewpoint. I think so. This abstract, what we peeled out was, if you feel like an anthropologist, you explore. You don't care. You don't run against the problem. You just want to understand, and every epsilon suddenly counts. Yeah, you feel like you made some progress today. Whereas if you are so problem directed and run against the wall, there's a fantastic amount of frustration. But there are people who like this. They run for a year against the wall, and then they manage to get through, and the amount of adrenaline is so fantastic. I think they're on a super high, and they love this. You know? So, there's this whole, so I changed to the Floer method, I must say. It's better for family life. I think it's more effective. Yeah? You're exploring things more and more, you have more interests, but you keep track of them, you hook them up, you work them, how you think about stuff, and then sometimes you can write something about it. It's more boring, yeah, but I think it's much more effective.
Another question by Patrick Morris. Maybe he just goes ahead himself.
Yeah, so I think I can read this.
You can read, okay.
He played gamba. So and I cannot say, so he had friends with whom he listened to music and with whom they played music. So there was a group, and I think in that group, they knew each other, of course, but some of them presumably didn't even know that he was a mathematician. I mean, when he lived in Berkeley, I mean, he had also these different groups, and I think they didn't know that he was actually already a famous guy. I mean, he had sort of this affinity with underdogs, for example. So there was a story told to me by a friend. So he was very generous with money. So he gave to the homeless people plenty in Berkeley. And he went shopping with a friend, and there was a homeless person who always had gotten a lot of money from him. And Andreas didn't have enough small bills. So he gave him a smaller amount. And this homeless person got really agitated and started to attack him because he got less money. He actually beat him up. Beat Andreas up. And then that was according to his friend, a fantastic shock for him, because he was sort of always nice, but he didn't have enough cash on him. And he went home and he was sitting there for hours silently. He didn't say anything. and and I think that was one of the things he couldn't. He had a difficult time to bringing his feelings out. So, and I remember, I think when I came to when I came to the MSRI, not the MSRI event. I came to the MSRI event, and of course at that point, the ATMs, international ATMs, and so or in ATM system wasn't that developed. So if you needed cash, so you went at that time. Kaplansky was the director of MSRI. You got a check, then you had to go downtown to a specific bank to get your cash. So I managed to arrive there basically without cash, and I knew Floer, so I asked him, can you give me some cash? So he goes in his pocket, hands me a bundle of money. Turns out it was over $1,000, and said, you think that's enough? So I thought that's strange. So it turned out then that a friend of his who wasn't that successful had told him he wants to start a company and he needed some startup money. And so Floer got cash to support a startup, and then the person didn't show up, which of course wasn't presumably the best person to run a company. So therefore he had this cash in his pocket and gave it to me. So it was quite interesting. So, but I cannot say more about music, but he definitely loved music, and he played music, and he had a group of people interested in classical music.
I do not see any further. There's another question coming up. When is this book coming out?
Siobhan, when is this book coming out?
Time will tell. Books are like marathons. They take a long time, and we both have other book projects on the go. So I think the estimated pub date is still unknown.
Yeah, so we are actually currently discussing that she comes to the Institute for a while. We have all the material, so I think we need some intensive 3-4 months to write it.
Yes, indeed. And with that, I actually have to run, conveniently enough. But thank you, Helmut, for the wonderful talk, and thanks to everybody for the great comments and questions. It's always great to collect more material. The details add up every time.
Thanks, everyone, for coming.
Bye.
Bye.
May I make some mathematical comment, yeah, because we were speaking about the past, but I think the message of the future is the work of Floer, is what the logic of that properly understood finite dimensional idea go to infinite dimension. And just recently there was a different development with the last couple of years coming from Scholze. They developed this potentially remarkable theory that looks at this very remarkable condensed spaces, which negates usual perspective on topology and possibly on Fredholm theory. So indeed, I'm always felt and feel that Fredholm theory is unduly narrow in the much broader and conceptual development. And when Helmut, you're developing your own theory of this kind. But Scholze gives much more general perspective in Grothendieck style, and it's very simple idea. Underlying idea is tremendously simple, and there may be a version of that. They kind of aimed on algebraic problem. They want to algebraize in the style algebraic geometry, but we may think from different terms. Our background is kind of dimensional spaces. There may be parallel theory in analysis, which would engulf Floer theory and gives a new, more broader perspective. This is what kind of we want all the time to do, to change our perspective from the spaces and the object we work with. We have the beautiful thing happening, but we never know what is the actual domain where they live, yeah? And this we want to determine, and Floer had done that for Morse theory for the moment, but it's certainly not the last word.
No.
The last word. There will be next step, even kind of more radical, and we have to look for that, but certainly there is no recipe for doing that. But Scholze, this may suggest a way of doing that. That's, I think, is a very grand idea, and you can see how much it may reverberate with what we do. You know, this basic idea is very extremely simple. You know, that any topological space or real space is a quotient of a Cantor space. But then you say, forget about this kind of quotient. It's just category of Cantor space may map to that given space. So there's a functor from this category of this profiled space to sets. Period. Pop. And then topology disappears all engulfed into this very algebraic setting. But there may be something of a in spirit closed by difference, specifically in the subject, which we can do, right? And all we are looking for that. We look for new concept of space, new concept of Fredholm, new concept of operator. Because definitely, when you think about that, they're not satisfactory. It's clear. They're just too technical. They're not just reflect fully what we want of them. And this, I think, the message we have to take from Floer, right? Or from Scholze and his who do it in the next level. So this is my kind of attitude. You look at Floer, you say, what is the next? Yeah, right? What is the next step? Right? Comparably, of course, you cannot put it out of your head. Yeah, it doesn't come easily. However, this is the world we do have. Yeah, the world of the future. Right? So, at the moment, I think we should think about this different directions. So of course there are other kind of ideas of from different people. Recently I learned that I was very excited about that, yeah, of these condensed spaces. So simple and so kind of radical, yeah. So engulfing. So
good that you say us here. We have so many graduate students now. They all start thinking about it.
Yeah, exactly. You have to think about it. You never happens if you don't think, yeah. So we, of course, a little bit past our best age for doing that, especially myself, yeah. But the younger people.
Yeah. I mean, I understand what you're saying. Yeah, maybe it's worthwhile to explore that direction.
Right. We want to see new perspective before we stop really thinking. Yeah, really like with Floer, with something next level, beyond horizon. Yeah. And
yeah, I mean, you definitely, I mean, of course, involved in trying to make it more like this Floer theory, like a Lego type system that you can recycle stuff and so on. And it is, of course, ultimately a language problem where you have, say, a rich language, a lot of moving pieces which are easy to understand. And out of this, you can construct complex things with ease. So that would be, I think, something which is a possible direction.
I say we don't know. We just have a dream. We don't know.
I know.
The moment you say it will be this, you're on the wrong track. Yeah.
No.
Background is not be different from what you know, right?
I understand, Misha.
I'm looking at what the anti people are doing.
Yes, right.
Like Scholze, yeah, this is really the kind
No. I understand that, but I think the fact that complex things have to be built out of smaller things and so on. I think in many cases you can agree on this, and that is particularly difficult in the smooth world. I think in this kind of setup.
But I'm actually thinking, if there isn't this smooth world counterpart of the Scholze modification, so you change your kind of.
No, I understand.
On one hand, you tremendously generalize it. On the other hand, to make it simpler. And this is what's happening. Of course, I don't understand only superficially what's happening there, but I mean, I just like looking at that. But this beautiful, simple, and just have this power. And there are examples in my experience that this may solve difficult questions, just changing completely how you think about them. Right? That's the whole point. We have goes on mode of thinking, and just during its work up to point, and then it always stop working. Again, physics give you the best example, like Einstein. You have it's a fantastic way of thinking up to a point. There it was kind of dead end, and this is true about everybody, right? So then the only way to break it is just to see what's happening around us, coming from a different domain, from younger generation. And this is, for the moment, maybe it's not the right thing, but it's one of the things I just want to bring to the focus, because in geometry and topology we usually are unaware of that, because there's different community. but it's have the same mathematics. Yeah. Anyway.
Mhm.
So what would growth index type mathematics of smooth spaces would be, right? Or Floer type mathematics or whatever, but something different.
Mhm.
Otherwise, it becomes boring, right? Having the same space all the time. How much you can stand with.
Mhm.
Okay, but it was a great lecture. Yeah, really inspiring. Yeah.
Thank you.
So I also have my now go to my kids. Yeah, sorry.
Thanks for coming, Misha.
But their patience was really to the extreme. Okay, so bye.
Take care. Bye, Misha.
Bye.
So Helmut, what do you think? I see no more questions or hands up or anything like that.
Yeah, so last call.
Okay.
So, but before you switch off, so let me thank all the participants. And there's still something like 88 people hanging around here, too shy to, and many of them too shy to ask questions. But I think it was really great that Misha came, and I think he had a good point there. So maybe the younger people, yeah, should look at the Scholze stuff, have also, have some Floer experience. Maybe there's something interesting language to be found to deal with this kind of problems. Yeah, so I mean, it's perfectly reasonable. And yeah, and as Karen said, very often the things come from the outside. Yeah? So,
well, I think it was a great remark, so to say, because this is really some kind of great contribution now to topology, so to say.
Yeah,
guys. Maybe someone re-explain what contribution Gromov meant from Scholze. I didn't quite follow.
Oh, condensed mathematics. So I think you can find that actually if you go on the archive. There's also presumably a recorded talk about this. There was a recent conference to support a Russian graduate student, and Scholze talked about condensed mathematics. So he does. Of course, we know for us a space, for many people, a space is a topological space, but he completely redoes this, and topological spaces still exist, but it's a bigger universe in which you can do a lot of new stuff. So you can take quotients which you would never take in topology and so on. So, and you can go on and on, maybe to completely new stuff and end up maybe at the end at something familiar, but it gives you much more freedom to do things. And it is redoing the fundamentals of a certain area of mathematics. What is a space supposed to be? So yeah, I downloaded something after hearing Scholze's talk, so I could relate to what Misha was saying. And Misha has always extremely good taste. So for the younger people, presumably running a seminar on the side and learn a little bit about condensed mathematics and do your symplectic geometry, and then, maybe something clicks, yeah? Maybe something clicks really big, yeah? And then somebody will give a talk about you in a few years, yeah? So, or after you, you better have a longer life than Floer. So, yeah, so I think what Karen said and Dusa said and Misha said, they're very seasoned researchers, and they have very, very good idea how research and discovery works. So I mean, even I listening to them found that very inspirational.
Yeah, Felix Schlenk just put the link into the chat, but you can also simply Google condensed math Scholze, and then you get videos of the lectures.
Yeah, and yeah, so I hope you had a good time, and maybe it sets an agenda. Yeah, the discussion which we had here. Yeah, it was a lot of fun. And I think, yeah, so when I look at the outcome of the discussion, one should have this type of talks really more often. Yeah, that somebody talks about the development of a certain area and just in an easily understandable way. And it resonates then to more people because they see that they start even in a different field about similar things, and it starts a discussion between different groups. I think that's really important. So I was definitely not expecting, even if I had looked a little bit, that Gromov would come up with the condensed mathematics and had some ideas, thought that it might be useful.
So this sets another agenda.
Yeah.
Helmut. Okay.
I think so.
Yeah. Okay. Yeah. Thank you from my side. Also, again, I think in the name possibly of all participants, I can say it was a great event, and maybe we stop at this point in time.
Okay.
Okay.
Bye, and have a successful day and weekend.
Attending.
Bye.